This is the acceptance test for MEC 442, Challenge 1. Our challenge is to program one PAC to control a robotic cell that contains a material saw, which cuts bar stock and feeds two different types of bar stock into one of two buffers, and then we have a CNC machine and a robot that are able to work independently of each other to process either material 1 or material 2 at the same time. Not either, I'm sorry, or they can process material 1 or material 2. Or they could use two machines to process one material if that's, if you need more of one material or the other. So let's go to our system map and we'll talk a little bit about architecture and methodologies. So first off, just as we use the system map to program, because that's what this one is supposed to help us with. It's sort of a programming challenge, not a machine documentation challenge. So I'm a big fan of redundancy here. So we have our tag table with all the addresses and the role / hierarchy. And then we have an SFC chart which contains here exactly the names and addresses of the tag table. We also have the same in our signal timing diagram. So no matter where you look to program, you have a lot of the same information. So you won't forget it. You can easily reference one or the other in your programming. System architecture. So one of the most important things I think here is the state of the machine and how they all interact. So the PAC controls all the handshake surfaces, and the PAC cannot reach inside to change the internal logic of the machine, but the machine has to send its commands to the PAC before doing anything. That is a feature of how they interact. So the robot, for example, could not load the material until CNC1 door is open and the machine is ready. The PAC is going to orchestrate all this. For example, the PAC sends machine start cycle. The PAC will authorize the cut only when ready and material present are true. So the saw is not going to cut with an empty material according to the PAC. Saw acknowledges start. It is taking control. PAC now backs off. The saw is going to flag that the cycle is running high and that the machine is busy, and the PAC will act on that. But it's not giving commands directly to the PLC, okay? System data, also called system overview. Here we have our data on the PLCs we're using. Output, input. And we have our data on the controller we're using. We got a little controller view. This schematic, I tried something different for each system map, and this was supposed to be me seeing how I could create a single line diagram. I actually used AI to generate this, so I was able to check with the other type of schematic I did. I'll talk about it later. But this one, it was kind of hard for me to double check because I'm not very good with electrical. So If I had time, I would probably do the same schematic that I did in Challenge 2, but nevertheless, code layout. Also, I came up with a better code layout for Challenge 2, but maybe we'll also change that if we have time. This doesn't include the variable blocks or really the timers, so it's incomplete and a little hard to read. And that's a little self-critique. Alright. Architecture, we're going to prioritize timing, safety, sort of a modular programming structure as well. So we're going to have the same variables shared across the namespace, except they are named so that we can easily tell which is which. Here we go. Alright, now, let's see how this works. So, a little note. I used Claude AI to do this, and I perhaps should have done it myself because it would have been easier. Maybe. I mean, it was a lot of battling for 10 hours with Claude to do this. However, that was partly due to the fact that for this simulation, I was actually programming all the internal logic myself, right? Claude was. It was a mess. We got our visualization here. Let's see how it works. We're already online. We're already fired up. Alright, when I press the start button, we're going to see the pack change state, the buffer counter go up. Both buffer counters go up. Start with buffer 2. Here we can see all of our tags. CNC1 machine ready. So the robotic arm is actually going to grab a part and start machining it. That's why buffer 2 count is going to drop down right as buffer 1 count also goes up. That is another feature that proves the cells can be controlled independently. Right, so buffer count go down. So here we are actually processing material 1 and material 2 from the same saw. Right. Now, another architectural safety feature is that when we press stop, the buffer keeps filling until it gets to 10, because that is actually a physical architectural interlock or safety feature, because we would want the saw to keep running or the robot to keep picking or placing a part, or the CNC machine to keep machining. I think that's how I designed it. I hope that's correct. Never really designed one of these robot cells before. Stop. This is why you're going to see it keep doing things. Robot goes through its cycle. Right. The machine finished machining. Everything turns off. Machine Ready. Alright. We start it back up again. Okay. That's good. Alright, now this is our fault security architecture. This is a force fault button. This light is going to come on when we press it. Boom. Everything drops back down. That looks good. Okay, so the architecture here is that the operator has to manually clear the fault, which would represent that the machine is fixed. Stop button doesn't do anything. Start button doesn't do anything when it's in a fault state. Excuse me. Fault acknowledge doesn't do anything. Clear the fault. The light won't go off until we hit fault acknowledge. Right? Start it up again. This is a logically sound program that you should be able to transfer to hardware fairly easy. Now, I know I had a problem getting the actual hardware to run. However, another colleague of mine ran into the same issue, which is why I'm just running a simulation mode to prove that I can generate some PLC programs. Now, the problem I was having with Claude was basically that it made these complicated programs that, quite frankly, it was hard for anyone to read and troubleshoot, including myself. So, but, you know, the basic structure is pretty similar here. I'm just going to go offline so we can look at it. State machine, variables, this is our new HMI. We got our buffer counts, buffer max, buffer low was ignored here because that is also our physical reality that the saw is cutting 10 bars at a time. So the buffer goes low when it finishes cutting a bar. These are tags here to check if a part was deposited into the buffer. Same here on the conveyor belt. These are some timers here. I think these are about 200 milliseconds. Scheduling. So, you know, this was pretty good. I was actually impressed with how Claude was able to interpret the system map. But I think I would like to try and spend a few minutes every day on my own programming so that I don't get de-skilled with the use of AI here. I'm pretty confident that if I was able to confirm there wasn't a hardware fault in the way the machines were set up in the lab, that I could have programmed it. However, I triple checked the logic and even copied some code that the professor slash instructor was using and tried to load it on the machine, and the code would always get stuck right before the machine start cycle phase. Load material would not change any of the inputs to the PLC when I hit that load material output, even though all the conditions had been met. But, you know, like I said, if that had been fixed, if my other colleague hadn't had the same exact problem, I'm sure I could have gotten it with a little more time. That's challenge 1. We have all the logic working. This Baroque code that good old Claude made for us. HMI. That's it for challenge 1. Thank you very much.